I'm Kristen.
Hi, I'm Mary Beth.
And we're the Auburn University Senior Design Project team working on safeguarding the robot in the Lego Lab.
Today we're going to show you around the robot cell and see what improvements that can be made.
Let's head on in.
Hey guys, so when it comes to robot cell hazards, you may not know exactly what can be considered a hazard, but as you can see, I can reach my whole arm into this cell opening, and if I was a small person, I could even reach my whole upper body into it as well. This can be a concern when we're working on the Lego cars in the Lego lab here on the Operator 15 workspace, so this is obviously not compliant with current standards.
One of the standards that we're mainly concerned with is the ANSI RIA R15 06 1999 10.9 standard. This standard, from the American National Standards Institute, states that special care should be exercised where an operator is required to interact with the robot on each operating cycle, such as to feed parts to the robot for processing, and that the user of the robot system shall ensure that safeguards are established for each operation.
In order to be compliant with the standard I just mentioned, we're going to have to install some more metal fencing, like the yellow fencing we have around here, and we're going to place it such that the only opening is just small enough to let a Lego car go through.
So as it sits right now, the operator at this station is the last line of defense between the line and the robot. It's pretty easy to imagine a situation where something inside the cell goes wrong, whether it be a part fall on the ground, the lines get tangled up, or something else like that. As it sits, there's nothing really stopping the robot from continuing to cycle. What's going to be an easy way for an operator right here to keep this from happening? So the answer is simple. The good way to eliminate the losses of the robot malfunctioning would be to install an emergency stop somewhere within the reach of the operator of this station. Not only is this the smart thing to do, it's actually the law. Standards adopted by OSHA from the American National Standards Institute tell us that each operator capable of initiating robot motion must have access to an emergency stop. Without installing one at this location, this system is out of compliance and is at risk for a citation from OSHA. Now that we know what to do, how exactly do we do it? Will any emergency stop work? Well, not quite. For an emergency stop to be used to control a robotic cell, 3 conditions must be met. The first condition that must be met is that the emergency stop must be red in color. The second condition is that the background of the emergency stop must be yellow in color. And finally, the third condition is that the emergency stop must be of Category 1 or Category 0, which guarantees the complete removal of power from the machine actuators. With regards to the inside of the cell, there's actually no standard that requires an emergency stop be placed inside. However, the team recommends that we place one in here just in case the primary safeguard, such as the scanner, fails.
When safeguarding a robot, figuring out what materials to use for a safety barrier is extremely important. A few examples are shown here. This top piece right here is plexiglass, and the bottom down here is metal fencing. ANSI/RIA 15.06 1999 10.7.7 covers barrier safeguards and distances for robotic safety. The standard states that 0.45 meters, 18 inches, or more clearance shall be provided from the operating space where feasible. Otherwise, additional safeguarding shall be provided. In accordance with the 10.7.7 standard from ANSI, there are 2 zones that we need to be concerned with. One is the work envelope, and the second is the restricted space. And this is super important when we decide what safeguards we put over here. So, this robot has a work envelope of approximately 46 inches. And with this standard, it shows that it needs to be an additional 18 inches beyond that for our safeguard to be placed. So this should be approximately 64 inches. However, this distance is only 32. Given the standards and the measurements, it's pretty clear that this front piece of plexiglass needs to be replaced. It needs to be replaced with metal fencing because it can withhold a lot more force. Secondly, this piece of plexiglass also needs to be changed to something stronger. Although the distance from the center of the robot to the far edge over there is pretty far, it's pretty close over here. It needs to be replaced with something like polycarbonate. A good reason to use polycarbonate would be that you could still see the robot and what's happening, which is super important in an educational environment. Finally, the back piece of plexiglass just needs to stay the way it is because it's well beyond 64 inches.
The Lego completes the process of inspecting the Lego car by putting it in one of two chutes. One chute is indicated for the good cars and the other is for the bad, and they exit through these holes. The holes are 6 inches tall and 5 1/4 inches wide, and your hand and arm can fit all the way through into the cell.
With regards to regular openings in robot cells, there are 2 standards we use to help make this space safe. OSHA 29 CFR 1910.217 gives a safe distance formula which regulates the distance between openings in the cell wall and the robot itself. The safe distance, also called DS, from the sensing field to the point of operation shall be greater than the distance determined by the following formula. DS is equal to 63 inches per second times TS. TS is the stopping time of the robot. ANSI R15.06 1999, or now called ANSI B11.19 2010, gives the minimum distance when reaching through a guard using the upper limb, which are based on anthropometric data of the human arm. Our hole in the cell is between 1.9 and 5.2 inches. Therefore, the safe distance is 36 inches or greater.
There are several ways to make these exits compliable under OSHA and ANSI standards. One would be to apply a light curtain. Another would be to apply a hood that makes it awkward for a spectator or operator to reach their hand inside the cell. And another would be a tunnel that extends the safe distance away from the hazard, which is the robot. We chose to do the tunnel because it was the simplest option for our project.
Currently, the primary method for safeguarding the robot cell is the Keyonce safety scanner. This safety scanner has an indicator light as well as 3 pre-programmed zones. The first zone flashes the indicator light green. This is the safe zone. This is when the door is completely shut and the robot is normally operating. Second is the warning zone. This is when the light flashes orange. The robot is being slowed. And lastly, the protection zone flashes the light red. This is when the door is opened and immediately the robot is stopped. This protects the workers and students in the lab from getting injured by the robot.
The ANSI RIA R1506 1999 5.3 standard covers area safeguarding devices. This standard states that there needs to be an indicator light on the safeguarding device. Additionally, the safeguarding device needs to be uninterrupted by environmental conditions.
Researching the safety scanner, the user's manual states that it complies with OSHA and ANSI standards. There is an indicator light at the front of the scanner, however it's very small and not that easily visible. The team suggests installing a larger, more noticeable indicator light, potentially around eye level. Secondly, the team suggests moving the scanner to around foot or ankle level so that upon entering the cage, the robot will immediately shut off.
Making these improvements would advance the robot cell to meet all OSHA and ANSI standards. Additionally, it will give IE students the opportunity not only to see the operations of the robot, but also learn the importance of robotic safety and the different ways to safeguard a robot cell. This knowledge is beneficial to the curriculum at Auburn University, as well as applicable in a manufacturing environment. War Eagle.